At NAB, I saw wireless time transfer tech that I hadn't heard of before. The tech is called Wi-Wi STAMP, and it lets you transfer a timing signal accurate down to less than 5 nanoseconds over the 900 megahertz band. I got to talk to Wi-Wi's co-founder Nobu at the Meinberg booth.
This technology is from the NICT Japan. NICT is they set the Japan standard time, so this is part of their sort of timing application. So what it does is there are 3 black modules, and their time or phase is synchronized. So the phase at the 920 megahertz, they do the communication over the 920 megahertz radio. And the phase of each 920 megahertz is exactly aligned with each other. So that makes this demo possible that every time, so this module spits out the packet like 20 times a second. So each packet is received by 3 modules. And since the clock are exactly aligned, by looking at the phase difference between these two gives you the vertical position. And the phase difference between these two gives you the horizontal position. And in the end, if you move sideways, you can see it move sideways, and if you move vertical, you see that, and of course, you can draw a circle as a combination. So this is really sort of, we take it as a byproduct of time synchronization. It's only possible because these 3 are synchronized at picosecond level. Also, we can sort of play with it.
So we can do the cup game.
Hey, which one?
Middle.
Yeah. There it is. You said picosecond time on these. What kind of internal clocks do they have?
So internal clock is actually 40 megahertz clock, but in order to make it a radio, the radio chip up converts it from 40 megahertz to 900 megahertz. Now, so the beauty of it is it's not aligning the 40 megahertz, but it's aligning at the 900 megahertz. So it's much more precise. And let's say it's 1 gigahertz, 900 megahertz is close enough. And if it's 9 gigahertz, 1 cycle is 1 nanosecond. And so the phase means that you are being able to resolve that 1 nanosecond at between with the signal to noise ratio of about 100 leads to 10 picosecond jitter in measurement of the phase.
So I guess my next question is, if you have Wi-Fi, which is 2.4 or 5 or 6 gigahertz, what's inadequate about that versus Wi-Fi?
Okay, so you can actually repeat this exact setup with the Wi-Fi 2.4 gigahertz or 5 gigahertz as well. But you cannot do it with the commercially available Wi-Fi chipsets, mainly because the oscillator is bad. So if you put the good oscillator, you can do exactly the same thing. And we have actually demonstrated that as well.
So you're basically saying the consumer router that you might have at your house, you can't guarantee that it's going to have a good oscillator inside of it. So you can't, there's no guarantees with the clock.
Yeah, at the moment, I can almost guarantee that they have bad oscillator.
So what is used in these? Is it a TXCO or is?
So we used to use the OCXOs, but now it's fine with TCXOs. Since they only care about the relative alignment, and they don't care about the long-term correctness.
Holdover.
Yeah. So TCXO suffices, and TCXO is much better in terms of the power consumption.
Cost and size and everything, yeah. So another question is what are the practical things? What is the first applications that this Wi-Wi STAMP has?
First thing is to align the timing. So I think the timing is really our first sort of application field that we should first pursue, because position is again byproduct of the time synchronization. So like we are at the nav hoping that we can align the time for the broadcasting, like a time of the camera, time of the switch, time of the sort of control system.
Yeah, well, and I noticed like some of the places that have the constellation of cameras too. I can imagine if each one of them had one of these, you could have that time data with the signal, and then you could reproduce that 3D space a lot easier.
Yeah, and there are a couple of vendors who does the video transfer over the air. So if we combine this time synchronization over the air with the video transfer over the air, then the camera can be freely mobile.
Can we open one?
So that's the OCXO.
TCXO, but
This is
it's a big one.
So I mean, this is the Wi-Fi.
The actual radio unit.
Yeah, which this is going to be converted to an ASIC soon.
Yeah.
And it gets much smaller. It becomes like one chip.
Yeah.
And the rest is just to support this, like a USB, to program, let's say, this or something. But
Yeah.
right now, it's only power, doing nothing.
And outside that little room, they had a live demo set up with Meinberg's timing gear synchronizing video blackburst signals wirelessly. I got to talk about it with Uriah, an FPGA engineer.
So here we have a leader connecting to two followers as our time reference. Each of those feeds a PPS signal into a different microsync, which is really just acting as a converter to blackburst. The blackburst signal is then fed one to our vision switcher here, and the other two to our cameras that are mounted up top. And each of those cameras is then going to output SDI back into the vision switcher. And so if everything is synchronized correctly, we should see no glitches as we switch between the two video feeds. So we don't see any here. So that means it's all working. We've got some wireless blackburst going on here. As far as we're aware, this is the first time anyone's ever done it. Maybe someone did it in their garage, 10, 20 years ago, but they never brought it out to anybody.
It's not commercialized.
So, exactly. It's not yet commercialized on this end either, but we're working towards that. As far as like the more technical side, it's running at a 920 megahertz base frequency for the communication. That is a US and our third of the world unlicensed band. It has the ability to go at 860 megahertz for the European market and that area. But for the most part, it's interfacing, it has sort of a handshake very similar to PTP. So it figures out how to match the phase and frequency and then outputs locked 1 PPS from there.
Does it generate its own local time source, or do you need world time or anything like that?
So right now, the ones that we have here in our demo are generating their own local time source. This leader here is what everything is running off of. The newer versions have their inputs, so you can, if you would like to, back it with some kind of GNSS system to be able to have a more exact reference of time.
So could these distribute both the frequency, phase, and the actual world time, or?
I think so. That's more of a Nobu question.
Yeah.
Currently, the ones that we have are accurate to about 30 nanoseconds with about 20 picoseconds of jitter. The newer versions that they're working on, if I remember correctly what Nobu was saying, they are in simulation accurate to about a nanosecond. He's fairly confident that in reality, with all of the other things that happen in the world, it'll be about 5 nanoseconds. It's once you start getting a thing to keep in mind that I used to be a teacher, so I always used to tell my students, a light nanosecond is a foot. So there's a lot of stuff that can happen at that scale.
Even cabling becomes an issue, the
Yep.
consistency of your cabling and all that.
Yeah.
So yeah, well, thank you.